Every single day, nearly 100,000 commercial flights take off around the world. Each one of them is powered by a fuel that was already old technology when the Wright brothers were still in grade school. A fuel that lit the streets of Victorian London. A fuel your great-great-grandparents used to see by at night. And without it, not a single one of those planes gets off the ground. Next time you stop at a gas station, take a moment to look at the pumps. Regular gasoline on one side, diesel on the other. These two fuels between them power almost every car, truck, and motorcycle on the road. They represent the backbone of ground transportation as we know it. Now imagine trying to drive a Boeing 777 up to that same pump. Neither of those fuels would do the job. Commercial jet engines do not run on gasoline. They do not run on diesel. They run on a fuel that most people instinctively associate with antique camping stoves and 19th century oil lamps, kerosene. The same basic substance that lit homes and city streets across the industrialized world long before electricity became commonplace. This raises an obvious question that surprisingly few people ever think to ask. Isn't gasoline what we associate with high-performance engines? Isn't it the fuel of sports cars, racing motorcycles, and machines built for power? Why would a multi-million-dollar jet engine, a piece of engineering so sophisticated it can push 400 people across an entire ocean in under 10 hours, rely on something people once used to light their living rooms? The answer involves physics, altitude, temperature, and one of the most counterintuitive lessons in the history of aviation engineering. The sky itself turned out to be the problem. And kerosene, of all things, turned out to be the solution. To understand why jets run on kerosene, it helps to understand that they didn't always. The earliest aircraft in history actually ran on gasoline, and perfectly reasonably so. The Wright brothers flew on gasoline. The brave and often short-lived fighter pilots of the First World War flew on gasoline. Their aircraft were powered by piston engines. Fundamentally the same mechanical concept as the engine sitting under the hood of a modern car. Gasoline worked well for those machines because those machines flew relatively low and relatively slow, in conditions that were not dramatically different from what a car engine experiences on the ground. Even today, small propeller-driven aircraft still run on a specially refined version of aviation gasoline known as avgas, a direct descendant of that original approach. But in the 1930s and 40s, aviation underwent a transformation so fundamental that it essentially became a different technology. Engineers developed the jet engine, a device that operates on principles entirely unlike a piston engine. A jet engine sucks in enormous volumes of air through its intake, compresses that air to extreme pressures, mixes it with fuel, and ignites the mixture in a continuous, sustained roaring combustion that produces thrust rather than rotational motion. The jet engine made flight faster, higher, and more powerful than anyone had imagined possible in the era of propellers. But as engineers began testing these machines under real flight conditions, specifically at the extreme altitudes where jet engines perform most efficiently, they discovered that the fuel which had powered aviation from its very beginning had a critical and potentially fatal weakness. Not a weakness in the engine. A weakness written into the laws of physics. As a commercial aircraft climbs toward its cruising altitude of around 35,000 feet, the atmospheric pressure surrounding it drops dramatically. At that altitude, the air pressure is roughly 1/4 of what it is at sea level. The air is thin, cold, and behaves in ways that have no equivalent in everyday ground-level experience. Here is where the physics becomes a pilot's worst enemy. Gasoline is a highly volatile fuel. Under normal ground conditions, that volatility is actually useful. It evaporates readily, mixes easily with air, and ignites reliably in an engine. But volatility has a dark side at altitude. Because of the combination of dramatically reduced atmospheric pressure and the extreme temperature swings encountered during a climb to cruising altitude, gasoline becomes prone to evaporating inside fuel lines and fuel system components before it ever reaches the engine. This can produce a dangerous condition called vapor lock, a situation where vapor bubbles form inside the fuel delivery system, disrupting the steady flow of liquid fuel to the engine and potentially starving it of the continuous supply it needs to maintain combustion. In a car engine on a hot day, vapor lock is an inconvenience. In a jet engine at 35,000 feet over the middle of the Atlantic Ocean, it is a catastrophe. Kerosene behaves fundamentally differently. It is a heavier, denser fuel with a significantly lower vapor pressure than gasoline. Even at the extreme low pressures encountered at the thin edge of the stratosphere, kerosene remains in stable liquid form. It does not want to evaporate prematurely. It flows smoothly and predictably through fuel lines and pumps, delivering a steady, uninterrupted supply to the engine regardless of the atmospheric conditions outside the aircraft. The sky tried to turn the fuel to vapor. Kerosene refused to cooperate. The altitude problem is only part of the story. The cold is the other half, and it is every bit as extreme. At typical commercial cruising altitude, outside air temperatures regularly fall to minus 50 degrees Celsius, occasionally lower, depending on the route and season. Most liquids that exist at room temperature would become a thick, sluggish semi-solid at those temperatures, completely useless as a fuel that needs to flow freely through pumps, filters, and injectors at high volume and high pressure. Modern jet fuel, which is highly refined kerosene, specifically engineered for the demands of high-altitude aviation, is formulated to have a freezing point of approximately minus 40 to minus 50 degrees Celsius, depending on the specific grade. The most commonly used commercial jet fuel, known as Jet A-1 and used by airlines operating international routes across most of the world, has a certified freeze point of minus 47 degrees Celsius. This means that at the coldest temperatures a commercial aircraft typically encounters in normal operation, the fuel remains liquid. It keeps flowing. The engines keep running. This level of cold weather performance is not something gasoline was ever designed or refined to achieve consistently. Kerosene's molecular structure, heavier carbon chains than those found in gasoline, gives it a natural resistance to the phase changes that would render lighter fuels useless in extreme cold. The same molecular weight that makes kerosene denser and more stable against evaporation at altitude also makes it more resistant to freezing in deep cold. The sky is thin and the sky is brutally cold. Kerosene handles both. There is a third dimension to why kerosene won the competition for aviation's preferred fuel, and it is arguably the most practically important of all: safety combined with energy density. Gasoline is, by any reasonable measure, a dangerous substance to have around aircraft on the ground. It is highly volatile, meaning it produces flammable vapors readily at room temperature. A fuel spill during ground refueling, a dropped tool striking a spark, a minor leak near a heat source. With gasoline, the margin between a ground incident and a catastrophic fire is uncomfortably thin. Kerosene has a significantly higher flash point than gasoline. The flash point is the lowest temperature at which a liquid produces enough vapor to ignite when exposed to an open flame. Gasoline's flash point is approximately minus 43 degrees Celsius, which means at virtually any temperature a human being might encounter, gasoline is producing ignitable vapors. Kerosene's flash point is approximately 38 degrees Celsius, meaning at room temperature and below, kerosene does not readily produce flammable vapors. You can drop a lit match into a pool of kerosene at room temperature, and it will extinguish. You cannot do that with gasoline. For an industry that handles enormous quantities of fuel on crowded airport ramps surrounded by passengers and ground crew, this difference in ground-level safety behavior is not a minor technical footnote. It is a genuine operational advantage that has prevented countless accidents over decades of commercial aviation. Yet despite its stability at room temperature and low altitude, kerosene burns with extraordinary intensity when atomized and injected under high pressure into the combustion chamber of a jet engine. The same fuel that is relatively safe to handle on the ground becomes a ferociously energetic propellant the moment it is converted to fine spray inside the engine. And then there is energy density, the amount of energy stored per unit of volume. Kerosene is denser than gasoline, meaning a given tank volume holds more energy in kerosene than it would in gasoline. For an aircraft attempting to cross the Pacific Ocean on a single load of fuel, that difference in energy density is not abstract. It translates directly into range. More energy per liter means more distance per tank. More distance per tank means routes that would otherwise require a fuel stop can be flown nonstop. And nonstop routes are faster, cheaper, and more commercially viable.